Hello, we will continue with data link layer of the OSI model. And for those who are new at this channel, please do not forget to subscribe for the new videos that are coming up and the videos that are uploaded. Every network has physical components and media connecting the components. Different type of media need different information about the data in order to accept it and move it across the physical network. Since data must have help to move it across the different media, is a data link layer that will provide this help. And in this video, we will explain how media access control in the data link layer supports communication across network. The topics that we will be explaining here is to describe the purpose and the function of data link layer in preparing communication for transmission on specific media. We will compare the characteristics of media access control method on WAN and LAN topologies. And we will also describe the characteristics and the function of the data link. The data link layer of the OSI model, as it is shown in the figure, prepares network data for the physical network. The data link layer is responsible for network interface card to network interface card communication. The data link layers will enable upper layers to access the media, where the upper layer protocol is completely unaware of what type of media is used to forward the data. We'll accept data usually from the layer 3 packets, IPv4 or IPv6, and encapsulate them into layer 2 frames. We'll control how data is placed and received on media. We'll exchange frames between endpoints over the network media. We'll receive encapsulation data, usually layer 3 packets, and direct them to the proper upper layer protocols. And we'll perform error detection and reject any corrupt frames. In the computer networks, a node is a device that can receive, create, store, or forward data along a communication path. A node can be either an end device such as laptop or mobile phone, or an intermediary device such as Ethernet switch. Without the data link layer, network layers protocols such as IP would have to make provisions for connection to every type of media that could exist along a delivery path. In the figure, it is explained how data link layer as layer 2 Ethernet destination and source network interface card information to a layer 3 packet. It would then convert this information to a format supported by the physical layer. Data link layer consists on two sublayers, as it is described in the figure. It's the logical link control and media access control. The logical link control sublayer communicates between the networking software at the upper layers and the device hardware at the lower layers. It places information in the frame that identifies which network layer protocol is being used for the frame, and with this information will allow multiple layer 3 protocols such as IPv4 and IPv6 to use the same network interface on media. The second one, the media access control, controls the network interface card and other hardware that are responsible for sending and receiving data on the wired or wireless LAN medium. The MAC address sublayer provides data encapsulation and also frame delimiting, where with this process provides important delimiters to identify fields within a frame. These delimiting bits provide synchronization between the transmitting and receiving nodes. Addressing, where we'll provide source and destination addressing for transporting the layer 2 frame between devices on the same shared medium. And also the error detection, where it includes a trailer used to detect transmission errors. Each network environment that packets encounter as they travel from a local host to a remote host can have different characteristics. For example, an Ethernet LAN usually consists of many hosts contending for access of the network media. The MAC sublayer resolves this. With serial links, the access method may only consist of direct connection between only two devices, usually two routers. Router interfaces encapsulate the packet into the appropriate frame. A switchable media access control method is used to access each link. In any given exchange of network layer packets, there may be numerous data link layers and media transitions. At each hop along the path, a router performs the following layers to function. We'll accept a frame from a medium, we'll de-encapsulate the frame, re-encapsulate the packet into a new frame, and forward the new frame appropriate to the medium of that segment of the physical network. And as you can see in the figure, the router has an Ethernet interface to connect to the LAN and a serial interface to connect to the WAN. As the router processes frames, it will use data link layer services to receive the frame from one medium, decapsulate it to the layer 3 PDU, recapsulate the PDU into a new frame, and place the frame on the medium of the next link on the network. And let's see how it goes. See, we got the packet and we will add the new frame for the next hop. As we mentioned before, the data link layer prepares network data for the physical network. It must know the logical topology of network in order to be able to determine what is needed to transfer frames from one device to another. These topics will explain the way in which the data link layer works with different logical network topologies. The topology of a network is the arrangement or the relationship of the network devices and the interconnection between them. There are two types of topologies used when describing LAN and WAN network. The first one is a physical topology, where we'll identify the physical connection and how end devices and intermediary devices are interconnected. The topology may also include specific device locations such as room number and location on the equipment rack. Physical topologies are usually point-to-point or star. And we have also the logical topology. The logical topology refers to the way a network transfers frames from one node to the next. This topology identifies virtual connection using devices, interface, and layer 3 IP addressing schemes. The data link layer sees the logical topology of a network when controlling data access to the media. It is the logical topology that influences the type of network framing and media access control used. Depending on how WANs are connected together, we use three common physical WAN topologies. The first one is point-to-point, and it is the easiest and the simplest and most common WAN topology. It consists of a permanent link between two endpoints. The second one is hub and spoke, and this is a one version of the star topology in which a central site interconnects branches sites through the use of point-to-point links. Branch sites connect, exchange data with other branch sites without going through the central site. And the last one is mesh topology. This topology provides high availability but requires that every end system is interconnected to every other system. Therefore, the administrative and physical cost can be significant. Each link is essentially a point-to-point link to the other node. We have even a hybrid, where it is a variation of combination of any topologies. For example, a partial mesh is a hybrid topology in which some but not all end devices are interconnected together. Physical point-to-point topologies directly connect two nodes. In this arrangement, two nodes do not have to share the media with other hosts. Additionally, When using a serial communication protocol such as point-to-point protocol, a node does not have to make any determination about whether an incoming frame is destined for it or another node. Therefore, the logical data link protocols can be very simple, as all frames on the media can only travel to or from the two nodes. The node places the frames on the media at one end, and those frames are taken from the media by the node at the other end of the point-to-point circuit. A source and destination node may be indirectly connected to each other over some geographical distance using multiple intermediary devices. However, the use of physical device in the network does not affect the logical topology as it is illustrated here. Adding intermediary physical connection may not change the logical topology. The logical point-to-point connection is the same. In multi-access LANs, end devices are interconnected using star or extended star topologies. In this type of topology, end devices are connected to a central intermediary devices, in this case, an Ethernet switch. An extended star extends this topology by interconnecting multiple Ethernet switches. The star and extended topologies are easy to install, very scalable, and easy to troubleshoot. But we have even legacy LAN topologies, where early Ethernet and legacy token ring LAN technologies included two other types of topologies. The first one is bus, where all end systems are chained to each other and terminated in some from on each end. Infrastructure devices such as switches are not required to interconnect the end devices. The legacy Ethernet networks were often bus topologies using coax cable because it was inexpensive and easy to set up. We also have the ring topology, where end systems are connected to their respective neighbor, forming a ring. The ring does not need to be terminated. Unlike in the bus topology, legacy fiber distributed data interface and token ring network used ring topologies. So these are the LAN topologies, and we will continue with half and full duplex communication in the next slide. Understanding duplex communication is important when discussing LAN topologies because it refers the direction of data transmission between two devices. There are two common modes of duplex. The first one is hard duplex communication, where both devices can transmit and receive on media but cannot do so simultaneously. Wireless LAN and legacy bus topologies with Ethernet hubs use the half duplex mode. Half duplex allows only one device to send or receive at a time on the shared medium. You can see the example here. So they can do one at a time. And the second communication is full duplex communication, where both devices can simultaneously transmit and receive on the shared medium. The data link layer assumes that the media is available for transmission for both nodes at any time. Ethernet switches operate in full duplex mode by default, but they can even operate in hard duplex mode if they are connected to a device as Ethernet hub. As you can see the example here, they can send or receive at the same time. In summary, we can say that hard duplex communication restricts the exchange of data to one direction at a time, and the full duplex allows the sending and receiving of data to happen simultaneously. It is important that two interconnected interfaces, such as host network interface card and an interface on the Ethernet switch, operate using the same duplex mode. Otherwise, there will be a duplex mismatch, creating inefficiency and latency on the link. Ethernet LANs and wireless LANs are examples of multi-access networks. A multi-access network is a network that can have two or more than one device attempting to access the network simultaneously. Some multi-access networks require rules to govern how devices share the physical media. There are two basic access control methods for sharing media. The first one is connection-based access, where the multi-access networks all nodes are operating in hard duplex, competing for the use of the medium. However, only one device can send at a time. Therefore, there is a process if more than one device transmits at the same time. Examples of connection-based access method include carrier sense multiple access with collision detection, usually used in bus topology Ethernet LANs, and carrier sense multiple access with collision avoidance used in wireless LAN. We also have the controlled access, where in the multi-access networks, each node has its own time to use the medium. This determines type of legacy networks are inefficient because a device must wait its turn to access the medium. Examples of multi-access networks that use controlled access include the legacy token ring and the legacy ARSNet. Today, Ethernet networks operate in full duplex and do not require an access method. This is only for explaining how it works. At the connection-based access, these networks operate in hard duplex mode, meaning only one device can send or receive at a time. This requires a process to govern when a device can send and what happens when multiple devices send at the same time. If two devices transmit at the same time, a collision will occur. So for legacy Ethernet LANs, both devices will detect the collision on the network. This is the collision detection portion of connection-based access. The network interface card compares data transmitted with data received, or by recognizing that the signal amplitude is higher than the normal on the media. The data sent by both devices will be corrupted and will need to be resent. We will explain this by an example. For example, we have the network and the PC1 will send a frame. The PC1 has an Ethernet frame that needed to send to the PC number 3. The PC1 network interface card needs to determine if any device is transmitting on the medium. If it does not detect a carrier signal, so if it's not receiving transmission from another device, it will assume that the network is available to send. So in this case, the PC1 network interface card will send the Ethernet frame when the medium is available. Then, the Ethernet hub will receive and send the frame. An Ethernet hub is also known as a multi-port repeater. Any bits received on an incoming port are regenerated and sent out all other ports as it is shown in this figure. If another device such as PC2 wants to transmit but is currently receiving a frame, it must wait until the channel is clear. And then is the last step where hub will send the frame. All devices attached to the hub will receive the frame. However, because the frame has a destination data link address for the PC3, only that device will accept and copy in the entire frame. All other device network interface card will ignore the frame since the frame is not for them. This can be shown even in the figure. Another form of connection-based access is for the wireless LAN, where is with carrier sense multiple access collision avoidance. In this method, it's similar to the collision detection to detect if the media is clear, but with additional techniques. In wireless environment, it may not be possible for a device to detect a collision. The connection-based access with collision avoidance does not detect collision, but attempts to avoid them by waiting before transmitting. Each device that transmits includes the time duration that it needs for the transmission. All the other devices receive this information and know for how long the medium will be unavailable. As it is shown in this figure, if host A is receiving a wireless frame from the access point, host B and C will also see the frame and how long the medium will be unavailable. After the wireless device sends the frame, the receiver returns an acknowledgement so that the senders know that the frame arrived, and whether it is an Ethernet LAN using hubs or wireless LAN connection-based system do not scale well under heavy media use. We have to explain even this, that Ethernet LAN using switches do not use a connection-based system because the switch and the host network interface card operate in full duplex mode. And this is all about the connection-based access with collision detection and collision avoidance. Where the collision avoidance we mentioned that is in the wireless LAN networks. The topic discusses in detail what happens to the data link frame as it moves through a network. The information appended to a frame is determined by the protocol being used. The data link layer prepares the encapsulated data for transport across the logical media by encapsulating it with a header and a trailer to create a frame. The data link protocol is responsible for network interface to network interface communication within the same network. Although there are many different data link layer protocols that describe data link layer frame, each frame type has three basic parts. They have header, data, and the trailer. Unlike other encapsulation protocols, the data link layer attempts information in the form of a trailer at the end of the frame. All data link layer protocols encapsulate the data within the data field of the frame. However, the structure of the frame and the fields contained in the header and trailer vary according to the protocol. There is no one frame structure that meets the needed for all data transportation across all type of media. Depending on the environment, the amount of control information needed in the frame varies to match the access control requirements of media and logical topology. As it is shown in the figure, in a fragile environment, more controls are needed to ensure the delivery. The header and trailer fields are larger as more control information is needed. Framing breaks the stream into decipherable grouping with control information inserted in the header and trailer as values in different fields. This format gives the physical signal a structure that are recognized by nodes and decoded into packets to the destination. The generic frame fields are shown in the figure. Not all protocols include all these fields, but the standard for a specific data link protocol defines the actual frame format. And we have the frame start and stop indicator flags used to identify the beginning and the end of limits to the frame. Addressing indicates the source and destination nodes on the media. Type identifies the layer 3 protocol in the data field. The control where it identifies special flow control services such as quality of service. Quality of service giving forwarding priority to certain types of messages. For example, voice over IP frames normally receive priority because they are sensitive to delay. data will contain the frame payload. It's the packet header, segment header, and the data. Error detection include after the data to form the trailer. Data link layer protocols add a trailer to the end of each frame. In a process called error detection, the trailer determines if the frame arrived without error. It places a logical or mathematical summary of the bits that comprise the frame in the trailer. The data link layer adds error detection because the signals of the media should be subject to interference, distortion, or loss that would substantially change the bit value that those signals represent. A transmitting node creates a logical summary and content of the frame, known as the cyclic redundancy check value. This value is placed in the frame check sequence field to represent the content of the frame. In other Ethernet trailer, the frame check sequence provides a method for the receiving node to determine whether the frame experienced transmission errors or not. The data link layer provides address in use in transporting a frame across a shared local media. Device addresses at the layer are referred to as physical addresses. Data link layer addressing is contained within the frame header and specifies the frame destination node on the local network. It is typically at the beginning of the frame, so the network interface card can quickly determine if it matches its own layer 2 address before accepting the rest of the frame. The frame header may also contain the source address on the frame. Unlike layer 3 logical addresses, which are hierarchical physical address, do not indicate on what network the device is located. Rather, the physical address is unique to the specific device. A device will still function with the same layer 2 physical address even if the device moves to another network or subnet. Therefore, layer 2 addresses are only used to connect devices within the same shared media on the same IP and network. We have the figure that illustrates the function of layer 2 and layer 3 addresses. As the IP packets travel from host to the router, router to the router, and finally router to the host, because those will be shown in the next slide. At each point along the way, the IP packet is encapsulated in a new data link frame. Each data link frame contains the source data link address and the network interface card sending the frame, and the destination data link address of the network interface card receiving the frame. So we'll start the communication from host to the router. So we want to see the PC1 need to send a frame to the final destination, which is the web server. The source host encapsulates the layer 3 IP packets into layer 2 frame. In the frame header, the host adds its layer 2 address at the source and layer 2 address of router 1 as the destination, the network interface card that is connected with the LAN that is the PC1, as it is shown in the figure. When the frame goes to the router 1 encapsulates the layer 3 IP packets into a new layer 2 frame, and in the frame header, R1 adds its layer 2 addresses as the source and the layer 2 address of router 2 as the destination. It will be the network interface card that is connected with the same LAN with the router 1. And finally, router 2 encapsulates the layer 3 IP packets in a new layer 2 frame. In the frame header, R2 adds its layer 2 address as the source and the layer 2 address of the server as the destination. The data link layer addresses is only used for local delivery, remembering that. Addresses at this layer have no meaning beyond the local network. Compare this to layer 3, where addresses in the same packet header are carried from the source host to the destination host, regardless of the number of network hops along the route. If the data must pass into another network segment, an intermediary device such as router is necessary. The router must accept the frame based on the physical address and de-encapsulate the frame in order to examine the hierarchical addresses, which is the IP address. Using the IP address, the router can determine the network location of the destination device and the best path to reach it. When it knows where to forward the packet, the router then creates a new frame for the packet, and the new frame is sent onto the next network segment toward its final destination. Ethernet protocols are used by wired LAN. Wireless communication fall under wireless LAN protocols. These protocols were designed for multi-access networks. One traditionally used the other type of protocols for various types of point-to-point, hub-spoke, and full mesh topologies. Some of the common WAN protocols over the years have included point-to-point protocol, high-level data link control, frame relay, asynchronous transfer mode, X.25. These layer 2 protocols are now being replaced in the WAN by Ethernet. In a TCP/IP network, all OSI layer 2 protocol work with IP at layer 3 of OSI model. However, the layer 2 protocol used depends on the logical topology and the physical media. Each protocol performs media access control for specific layer 2 logical topology. This means that a number of different network devices can act as a node that operate at the data link layer when implementing these protocols. The layer 2 protocol that is used for a particular network topology is determined by the technology used to implement that topology. A LAN topology uses a high bandwidth technology capable of supporting large numbers of hosts. The relatively small geographic area of LAN and its high density of users make this technology cost effective. However, using a high bandwidth technology is usually not cost effective for ones that cover large geographic areas. The cost of the long distances physical link and the technology used to carry the signal over those distances typically results in lower bandwidth capacity. The difference in bandwidth normally results in the use of different protocols for LANs and WANs. Data link layer protocol includes Ethernet, 802.11 wireless point-to-point protocol, high-level data link control, frame relay. If we see the animation, we will see even the layer 2 protocols that are used to transmit frame in different kind of communication. So we saw that we use different layer protocol to transmit the information from the source to the destination. This was all about the data link layer. Do not forget to subscribe at my channel for the new videos that are coming up and the videos that are uploaded for the moment. And thank you and see you to the next session.